All right. Hello, everyone. Let me know if you can hear me. Let me know if the music is too loud. Happy to be here today. So today I'm going to be talking about, well, how to turn your favorite image into a prime number. Hold on. Let me pull up the actual thumbnail that I made for this video so you can see it enlarged. Let's see. So yeah, if you look at this thumbnail, you'll see that this is an actual number we have over here. I hope you can see the resolution over here. So it's a 4,900 digit number, and this number happens to be a prime number, and it also happens to look like one of my two beautiful cats that you can see over here. So I want to talk about today how I did this, and you'll be surprised to hear that it's actually. Oh, by the way, hello, Farsad, and hello, Sophia. I hope you're well. And you'll be surprised to hear that it was actually not that hard to do this. It's kind of not that difficult. Not because, well, the reason is a lot of people have put in a lot of fantastic efforts into understanding prime numbers. And as a result, we know a lot about them, and I'm going to be taking advantage of a lot of that to come up with kind of a quick algorithm to turn your favorite picture into a massive prime number. So that's what we're going to be going over today. And also, if you have any other images you would like to suggest, I do have the code open. I can throw it in and generate a massive prime number of your choice. Okay, so in order to turn an image into a prime number, I guess there's kind of three ingredients that you need. First and foremost, you must just turn the image into a number. Or at least that's the strategy that I used. So you just take your favorite picture, and then you find a number. The size of that number must be a square. So the number of digits in that number must be a square. So I chose 4,900 because 4,900 is 70 squared. And the idea is that when you write all the digits of this number in a 70 by 70 grid or 80 by 80 grid or 60 by 60 grid, whatever the dimensions you chose, then it should look like the image. So I guess step one is to find a number that looks like your image. Okay, so you just need to find a number that looks like your image. Okay. This is not a particularly challenging step. Like, can't spell like. Your image, okay? And don't worry, I'll show you the code eventually. So the first step is, of course, you need to find a number that looks like your image. How do you do this? Well, here's the idea. You convert your image. Next step, claim it's prime. No, I swear. This is a prime number. Here, you might not believe me, so I'm gonna dispel your myths right now. So here's my number, cat prime. This is the number. Okay. So let me do a primality test on cat prime. Prime q, cat prime, and bam, there it is. I'm not lying to you. I'm not lying to you, Sophia. There it is. It's definitely a prime number. And just so you know, I didn't futz around with this. Watch. So if I do cat prime, why don't I change one digit? Just like one digit. I'll just change this 0 to a 1. Okay. And then I'll do a primality test on this. So. See, haha, it is no longer prime. So I swear this is a true primality test. If you want to, you can type this ginormous number into your favorite online primality tester and find that I am not, in fact, lying to you. Okay, so so once again, this is not a lie. This is not a mistake. This really is quite excitingly a prime number. Okay, it is a prime number that when you put it in a grid looks like my cat. As the thumbnail suggests. Okay, so in any case, step one is find a number that looks like your image. Okay, and step two is just find a prime number close to it. So you want it to be so close that it doesn't mess with the beauty of the image, essentially. Okay, find a prime number close to it. And that's it, really. You just find a prime number that's close to it. So you find a number that looks like your image and find a prime number that's close to it. So this is all, of course, easier said than done. I mean, you have to ask yourself the question, why is it so easy to find a prime that's close to the number that is shown in the image? Well, the first step is boilerplate. It's not that challenging. So let me talk a little bit about what the first step is. So all you really need to do for step one is you need to take your image, resize it to the size of the grid that you're interested in. So in this case, I went with 70 by 70, so it's a 70 by 70. So convert your image to black and white and resize it to 70 by 70, okay? Or 60 by 60, or whatever size you're interested in, okay? Now, retrieve the image data. So the image data will tell you kind of how dark each pixel is. And this will depend on how whatever image processing program you're using will give you image data that'll tell you the brightness of each pixel, essentially. So, I mean, I use Mathematica as usual, and so it basically gives you a number between 0 and 1, which tells you the brightness or darkness of each pixel, okay? So, you know, this will be like in my case, it was a 70 by 70 grid. And so you figure out the brightness and the darkness of each pixel. And the way Mathematica gives this output is it gives you a number between 0 and 1. And 0 means basically black, 1 means white, and a number between 0 and 1 is anything in between. If you use like OpenCL or Pillow in Python, or you use a different library in C++, you'll get a number between 1 and 256. That will tell you how bright your pixel is, 256 being the brightest, 1 being the dullest, okay? Once you have these numbers, you want to replace basically each of these pixels with a number so that, your grid of numbers looks a lot like your image, okay? So let's say this pixel over here has a brightness of like 0.4 or something like that, okay? So if this pixel has a brightness of 0.4, what you want to do in this situation is find a number so that if you were to draw the number as an image, its brightness is as close to 0.4 as possible, okay? So that's the second part. Just write out the numbers. 0, 1, 2, 0, 1, 3. We're having a good day today. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And then write them in your favorite font, kind of render them as images, and write down the brightness of each of these as like a square image or whatever in your favorite font. Okay? So, these numbers are written in your favorite font, and then you write down whatever their brightness is. Like maybe the 0 has a very, maybe 0 is very dim, so we'll say it's like 0.5 or something like that. 7 is very bright because most of the pixels in 7 are empty, so maybe it has a brightness of, I don't know, 0.9, and so on. And like I said, the units being used here will depend on whatever programming language or library is your favorite that you're using. And essentially, like I said, this part's pretty easy. So for each pixel, you find the entry in this table that's closest to it, and then you use that number. So if you stare at this, you'll find that in my preferred font, 7 was the brightest number, okay? Since 7 was the brightest number, all the white regions of the image got replaced by 7s. And it looks like here, if I'm not mistaken, 0 was my darkest number in my font. So all of the like dark portions of the image got replaced by 0. It's not that complicated. And so you can see the code over here. It's really not that bad. I have a picture of my cat. I brightened my cat's eyes just a little bit because when I did it initially, they came out as just like giant black blobs. So this is some Photoshop editing or whatever. Not trying to make all the other cats feel insecure or anything like that. But you start with an image. Try to pick a good image that has a lot of like light and dark regions. Also, let me zoom in a little bit so you can see what's going on. So try to pick an image that has a lot of light and dark regions so you get good contrast, and this process actually produces something beautiful. And so the first step is you just convert it to a grayscale image at the resolution that you like. So, you know, that should just be a couple lines of code no matter how you're working with it. Okay, this next line is I essentially sorted each of, so this is the font that I chose. This is the default Mathematica font. You can pick whatever font you like. I forget what this font is called. Coarser or something? I don't know, but it doesn't really matter. So you sort by the image intensity. So how bright each number is when rendered as an image. And so as you can see here, 0 was the darkest image, 8 was brighter, 9 was brighter, 6 was a little bit brighter. 7 is the brightest image because as you can see, it has the most white pixels. So I just sorted the numbers by their quote image intensity, which is a parameter that just measures how many, you know, kind of like bright pixels there are. Really not that complicated. And so these are all of their brightnesses printed out. So 0 has a brightness of like 0.57, 8 has a brightness of 0.6088, 9 has a brightness of this. And so I just made a nice little table that maps each brightness to the associated number. And then I just replaced so nearest is a function in Mathematica. There's something similar in like whatever programming language you use, you know. So nearest will replace, you know, every brightness with its closest number, and so you just run that over the image data, and you get a number, and that number is going to look like. So I stored all of that data in this number start. By the way, if any of you want this file, just let me know. I don't have a problem sharing it. You know, I've been threatening to make a like Davra Math GitHub page for a while now, but I'm also considering making all these code files available on Patreon or something if I ever bother to set one up. But in any case, this is the number start. So it looks kind of not like the cat right now because the width that it's rendering at is not the same as the width of the image. So what I need to do is I need to look at the integer digits of start, and then I need to partition them into a 70 by 70 matrix. And then I need to plot it as a matrix. Okay, and then, okay, so this should look more like my cat. It's a little big, so you can't see anything. But let me rasterize it. So let me convert it to an image so I can shrink it and expand it. So rasterize at there. Okay, and so you should be able to see my cat lurking in here. Oh, there he is. He's a good boy. So you can see my cat in here now. Also, I should have done the matrix form before I rasterize. So let me just do this. Okay, there he is. You know, looking good. When I put this in Photoshop, in order to get the digits to look more like the cat, I put all the numbers closer together. So there's a lot of white space, as you can see, the way it's being rendered in Mathematica. So if you look at each number, there's a lot of like white space between each number and each adjacent number, which kind of messes with the appearance of this thing over here, which of course I didn't like. But in Photoshop, if you like print the whole thing out, it has a command which lets you change the spacing between line to line and also from character to character. So I use the same font, but I reduce the spacing, and that's why this is looking so much better. Because you can see the digits are way closer to each other, and you know I think that gives it a more kind of a more natural appearance, essentially. Okay. All right. So I hope the first part of this is relatively clear to you guys. It's not too hard to kind of generate a number which when plotted or like which when written in a grid gives you an appearance similar to whatever image you started with. And of course, if you're in chat at all, if you have an image you're interested in having me do, then please let me know. I'm more than happy to do it. But regardless, hopefully this does not seem too crazy to any of you guys. Okay, so there's that. We've turned our we've done step one now. We've turned our image into a number. Now this next part is kind of shocking that you can even do this in the first place, okay? This next part is really quite shocking because, of course, the next step is to find a prime number that's as close as possible to this image. And so I'll have you know that this was not my original idea. Can we try Windows logo? Absolutely. I'll do the Windows logo. Here, let me look up a good picture of the Windows logo. Which one? Do you want the old one or the new one? Let's do the new one. Okay, I have copied the Windows logo for you, and okay, I'll do I'll do Linux as well. I don't want to, I don't want anyone to come at me after me with pitchforks or whatever. But here, I don't want to lose my cat, so I'll save my cat as image 2, and then but image can be image resize. We'll do 70 by 70, the Windows logo. And I just pasted this from my browser. Okay, there you go. There's a Windows logo. Okay, it seems like we have consensus on the Linux Penguin, though I'm already in this, so let me just finish this. I'll do that one as well. Okay, so you have this. Everything else here is the same. So let's see. So start is this. What happened? Hold on. Oh, I didn't convert it to grayscale. My bad. So what now? Hold on. Make sure all these steps are good. Image dimensions of image. It is 70 by 70. That's good. Okay. This is kind of annoying. I need to edit a little bit of the code. So what's going on here is that my original image had what's called an alpha channel, which says how transparent each of the pixels are. But this code, so all this code is assuming the existence of an alpha channel, which does not exist. So everything else here is fine. Okay, so this will be annoying. Remind me to put the alpha channel back in because it'll... Okay, that worked. So start is, I need to get rid of the alpha channel. Okay, cool. So let's take a look at this number start. So start is the number from which I start my, oh my goodness, my caps lock is on. S-T-A-R-T. Okay, so this should be the Windows logo. Let me render it properly. So integer digits, start, and I want to partition it into a 70 by 70 grid, right? Actually, wait, do I have that code sitting around still? No, I deleted it. Okay, it's fine. So I partition this into a 70 by 70 grid. Then I look at it as a matrix, and then I rasterize it. So I can zoom in and out, basically. So, okay. Let me zoom out a bit. Ooh, the resizing looped it, but you can see the Windows logo in there. So it like looped around the edge when it did the resize, but you can definitely see the Windows logo in there. Okay, so hopefully that makes sense. And of course, the next step is just finding a prime number close to this number. So, I mean, I wrote this all last night, so it's a little hacky, of course. But hopefully that all makes reasonable sense to you guys. And of course, you could do the Linux Penguin as well. The idea, again, is very simple. You find in your favorite font, you just map each pixel to the number that has the closest brightness to whatever you are interested in, okay? So I'm gonna go back to my original image instead of the Windows. I just like my cat more than the Windows logo. So, well, what happened here? Oh, I need to redo everything now. All right, so I went back to my original image. I've converted him to grayscale. The dimensions are good. Oh, I see what happened. Okay, so everything should be good. I should have also still gotten rid of my cat's alpha channel. This is start. Okay, yeah, he's looking good. He's looking like a good boy. All right, there it is. So my cat's still alive. Everything's good. Okay. Now I want to get to the next part of this, which I think, yeah. So it turns out when you enforce a dimension, 70 by 70, apparently it gets rid of the alpha channel for you, which is cool. So with an alpha channel, it would be 70 by 70 by 1. So the minute I said 70 by 70, it automatically got rid of the alpha channel, which is great. So as you can tell, of course, this is atrocious code. You have to like remember everything that you're doing. There's like no comments whatsoever, but whatever. So we have our cat. It's looking good. Life is good. Now we need to find a prime number close to this number. So there's a lot kind of going on here that I want to discuss a little bit. Why is it possible to find a prime number close to like the Windows logo works so well? It's actually, so what you need is high contrast, right? You want an image that which has a lot, kind of like bright pixels and comparatively dark pixels. And at the very least, the Windows logo does have that property, right? It looks like, oh, why did I try to draw? What am I doing? Why did I try to draw? But when you look in the, so the pixels in here are a lot brighter than the pixels on the outside. So you get that contrast, and because that contrast exists, the regions outside of these little blocks will map to different numbers than the regions inside, and so it works fairly well. It's not. It's actually pretty believable that it would work well. The worst case scenario for this methodology, it would be an image where there are not as many light and dark parts. There's this old Italian Renaissance painting style. I believe it's called chiaroscuro. If any of you know what I'm talking about, which has a lot of light and dark patches. So that sort of thing would be ideal for this methodology. Whereas, I don't know, maybe like an impressionistic painting or something would be the worst case scenario for this methodology. Any case, I've said a lot. Why am I so confident that it is possible to find a prime number close to my starting image? Now, if you think about it, the starting image is a 3,600 digit number. That is a huge number. I mean, the entire population of planet Earth is I don't know, smaller than the first 7 numbers over here. I'm sorry, the first 10 numbers over here, right? So that's just to give you a sense of how huge this number is, right? So why am I so confident that I should be able to find a prime number around this number? Well, my confidence is due to no effort of my own, okay? My confidence is due to this incredibly powerful, super duper powerful theorem called the prime number theorem. Okay, so the prime number theorem is one of those crowning jewels of mathematics. It's super crazy. I don't know how anyone managed to figure it out. Well, I mean, there are a lot of proofs out there. And interestingly enough, I think most people who prove this wind up living a really long time. So if you want the key to leading a long life, all you need to do is find a new proof of the prime number theorem that's interesting, and you might also live past 100 years, or so that is the legend, I hear. What is the prime number theorem? The prime number theorem can be stated in a lot of different ways, and to be honest with you, I'm not the biggest expert on this stuff. So the prime number theorem, I'll just say the consequence of it, or the consequence of the prime number theorem that's relevant for us. So if you pick an n-digit number at random, so if you pick an n-digit number at random, okay, then there's going to be a 1 over n natural log of 10 chance that it's going to be prime. Okay, let that sink in your head. I mean, that's a pretty strong claim. And I'm not being 100% technically precise, but you will see that it will absolutely pan out for us when we start searching for primes. Okay, so if you have an n-digit number at random, if you pick an n-digit number at random, there's a 1 over n natural log of 10 chance of it being prime. By the way, the natural log of 10 is 2.3. So it turns out there's a 1 out of 2.3 times the number of digits chance that a randomly chosen number will actually be a prime, interestingly enough. Okay, all right, that's interesting. Which means, how many guesses will it take? How many n-digit guesses will it take before I find a prime number? Well, approximately 2.3 times n, okay? It should take me about this many guesses, maybe a little less, maybe a little more. It should take me about this many guesses to find a prime number, okay? So, in under 10,000 guesses, I should be able to find a prime number close to my starting digit. How wild is that? I mean, so what makes this easy is that we're using the real firepower. You know, we're using a very powerful idea, a very powerful result, okay? Where we're bringing out the big guns over here. So in only 2.3 times n guesses, approximately, if we're honest about our randomness, if we really do guess randomly, we should be able to find a prime number close to our starting digit, okay? Interesting. Okay. That's one ingredient of this. Okay, so you know, in under 10,000 guesses, I'm guessing, I should be able to find a prime number close to my starting cat number. Okay, that's very powerful. That's very, very powerful. But there's another problem. Okay, so fine, you know, maybe I'm fairly confident that in less than 10,000 guesses, I should be able to find a prime number that's close to my starting number, okay? Not in less than 10,000 guesses, I should be able to find a prime number that's close to my, what was it? It wasn't 3,600 actually, it was a 4,900. Okay, so it'll be a little higher than that. Okay, I'll say less than 15,000 guesses. I should be able to find a prime number that's close to my starting number, okay? Less than 15,000 guesses. That's really fantastic news, honestly. I mean, that's pretty powerful stuff. But here's the problem. If it takes you forever to tell if a number is prime, then that 15,000 is a lot. Yeah, I agree with you, Sophia. That's extremely surprising. So if it takes you a really long time to tell if a number is prime, then it doesn't matter if it's 15,000 or if it's 15. You're in trouble, right? But the wild thing is, and this is extremely counterintuitive when you think about it, for some reason, we have at our disposal incredible algorithms to tell if something is prime or if something is not prime, okay? So as an example, at the very start of this video, when there were doubters, I put in a 4,900 digit number into my computer, a literal 4,900 digit number into my computer. And I asked it if it was prime. And it wasn't just instantaneously. It said no. Literally instantaneously it said no. I mean, how much time did this actually take? Let me see. Absolute timing. Okay. In 0.00001 seconds, it was able to tell me that this number is not prime. Isn't that crazy? I mean, here, let me modify it. Change this. I added a digit. I made it even bigger. Again, in the same amount of time, it was able to tell me that this is not prime. Okay? That's wild, right? I feel like this should be surprising to you. I mean, this is a big number, right? But it was able to tell me very quickly that this is not prime. What if it is prime? Okay, like what if I put in the actual number that I used to construct this image? No, I swear it's not. You can do this on your computer too. You can test it yourself as well. So if I actually put in the cat prime is the number that I'm using. So this one took a little longer, okay? It actually took about 20,000 times longer. Still very fast, okay? It was able to tell me in about 2 seconds that a number was prime, and it only seems to take it 0.00001 seconds to tell when a number is not prime. Okay, come on, that's wild, right? What is happening here? By the way, if this were not the case, if it were not possible for this thing to so quickly rule out numbers as not being prime, I would not be able to make this video for you guys. Okay, it would quite simply not be possible. Okay, so why are there such good ways to rule out numbers as being primed? And it turns out there's a whole like Alice in Wonderland rabbit hole of amazing primality tests out there. But I do want to make a quick distinction for you guys. The distinction is like factoring a number versus telling if a number is prime. Factoring a number versus telling if a number is prime, okay? Telling if a number is prime. Okay, I want to point out to you that these are two kind of different questions, okay? And if you had a fast way to factor a number, you would you'd be very rich and also probably dead, because if you had some methodology to factor a number, you would be able to crack RSA, which is like the cryptography method that's used to encrypt all our emails and web traffic and so on. So this is a whole interesting problem here. Like, if given a large number, can you factor it? So a lot of our amazing cryptographic algorithms rely on the fact that it's very difficult to come up with a way to factor and so like I hand you a random number. How do you factor it? Okay. The other hand, the other situation is telling if a number is prime. Okay, this is a whole different thing, and I'm going to rephrase this even a little bit. It should be the same question, but telling if a number is not prime. Okay, this is the rephrasing that we'll be interested in, and so as you can imagine, people have put a lot of effort into this, and I spent some time yesterday reading about it. I'm definitely not an expert by any stretch of the imagination, though I was extremely impressed with how clever people are in coming up with tests that tell if a number is not a prime. And so I know, so we don't actually know what algorithm my computer is using. Mathematica is not open source, so I don't know what algorithm my computer is using, though there are tons of fantastic algorithms out there that will just instantaneously tell you if a 4,900 digit number is not a prime, okay? It's amazing that stuff like this even exists. And so there's actually one, I wanted to give you guys some idea of what these algorithms are, what they look like. How is it possible that my computer can, and even your computer can, in 0.00001 seconds, tell you that a 4,900 digit number is not prime? Isn't that insane? How? So there's a lot of tests out there that exist for this, but there's one in particular that I feel like is understandable in the given time. So I'm going to talk about the Miller-Rabin primality test. Okay. Miller-Rabin primality test. Okay, so this is a very curious little primality test, and I'm pretty sure it's playing a role in why my computer and your computer can so quickly tell if a 4900 digit number is prime or when it's not prime. Okay, so what is the Miller-Rabin primality test? And once again, this is one of many possible, just kind of amazing probabilistic primality tests that are out there. Okay, here's the idea. I'm gonna say something right now. Let's say I give you a number n. Okay, actually, let's say p is prime. Okay, then this equation, x squared is congruent to 1 mod p. I'll write it without the mods too, in case you're not familiar, but I'm gonna write it first with the mods. Okay, x squared congruent to 1 mod p has only 2 solutions, namely 1 and -1. Okay, x squared being congruent to 1 mod p has only 2 solutions, namely 1 and -1. How would you say this without without modular arithmetic, in case you're not familiar with it? So what I'm saying essentially is that the prime number p divides x squared minus 1 if and only if it divides either x minus 1 or x plus 1. Okay, it divides x plus 1 or x minus 1. Hopefully this second way of writing it is clear to you, even if you're not familiar with modular arithmetic. Okay, so x squared minus 1 factors into x plus 1, x minus 1, and you know if a prime divides the product of two numbers, a and b, it ought to divide one of them because primes cannot be split further. Yes? So this is an interesting property of primes that's useful in this Miller-Rabin primality test. Okay, if a prime divides x squared minus 1, then it has to divide x plus 1 or x minus 1. The other way to say this is that x squared being congruent to 1 mod p has only 2 solutions, namely 1 and -1. Okay, I'm probably going to lean a little bit more on the side of using modular arithmetic just because it's easier to write things. But just so you know, if I say something like a is congruent to b mod n, all I'm saying is that a and b have the same remainder when you divide them by n. Or another way of saying this is that a minus b is divisible by n. So this is just shorthand for a minus b is divisible by n. And so this is saying x squared minus 1 is divisible by p if and only if, x plus 1 or x minus 1 is. Okay? So not too fancy. So we're really resting on this fact that x squared being congruent to 1 mod p has only 2 solutions, namely 1 and -1. Okay, so how does this factor into this Miller-Rabin primality test? Okay, I'm gonna let you in on a little secret that might be interesting to you if you take a lot of math competitions, but 2021, let's see, what do you think? Is 2021 a prime number, or is 2021 not a prime number? Okay, let's try and figure this out. Okay, using the Miller-Rabin methodology. Okay, so we're using the Miller-Rabin methodology to figure out if 2021 is a prime number. Here's what we're gonna do. First step, subtract 1 from 2021. You'll get 2020. Okay. All right, now you have 2020. Now, factor out as many 2's as you can from 2020. So I can factor out a 2 once, and I will get, 1010. And I can factor out a 2 again, and I get 505. Okay, so there's 2 2's that I can factor out of 2020. In other words, 2020 is actually equal to 2 squared times 505. Okay. Hopefully I'm not blowing anyone's mind right now with my amazing arithmetic. So 2 squared times 505. Okay. And essentially the numbers that we are going to think about are 505, 1010, and 2020. Okay. Now here's what we're going to do. We are going to think about what happens when you raise a number to these numbers mod 2021. Okay, so you will pick a random number between 1 and 2021, call it A, and then what we are going to look at is A to the 505, A to the 1010, and A to the 2020. Okay? Hopefully that all makes sense. So pick a random non-zero number, and then A. So we're picking a random non-zero number A between 1 and 2020. So A is, random between like 1 and 2020. Okay, is the idea. So I'm picking A as a random number between 1 and 2020, and then I will consecutively raise A to 505, A to 1010, and A to 2020. Okay, so that might seem like a lot, but remember, we're doing these mod 2021, so I'm not interested in actually what A to the 505 is. I'm interested in the remainder when you divide A to the 505 by 2021, which is a lot easier to figure out. Okay, so the numbers that I'm actually interested in are, let's see, it's A to the 505 mod 2021, A to the 1010 mod 2021, and A to the 2020 mod 2021. Okay, so this is the first number I'm interested in. This is the second number I'm interested in. This is the third number I'm interested in. Okay, let me know if that makes sense, or if you have any questions about this. So this is very simple to obtain. Take 2021, subtract 1, and then factor out as many 2s as you can until you hit an odd number. And then pick a random number and then raise it to those powers, mod 2021. Okay. Now here is the thing. Here is the thing that I want you to note. First and foremost, A to the 2020 has to be 1. This has to be 1. So what I'm saying is the remainder when you divide A to the 2020 by 2021 has to be 1. Okay? This is called Fermat's little theorem. It's not that hard to prove. Let me know if someone wants to see a proof of this. But if you raise any number to a prime minus 1 modulo a prime, right? You always get 1. So the remainder when you divide A to the p minus 1 by p is you always get 1 over here. It's a little bit tricky. You need to know like a small amount of number theory, right? But I guess take it as a given from me that if 2021 were prime, then we would know immediately that A to the 2020 would have to be 1, okay? But now look at the number before it. The number before it is a number that if I square it will give me A to the 2020, right? Which means if 2021 were prime, then this number could only be plus or minus 1, okay? This number could only be plus or minus 1 because remember, there's the only number that squares to 1 modulo a prime is 1 or negative 1. We talked about this earlier. So you can basically examine these numbers, and the minute you hit something that's not 1 or negative 1, you know that this number could not be prime, okay? And that is the essence of the Miller-Rabin primality test. And please let me know if you have any questions about this. So I guess you have to take it as a given that I'm telling you that if 2021 were prime, A to the 2020 would have to be 1. It might not be because I guess we don't know right now that 2021 is prime or not. Well, I know because I already did it, but you might not know if 2021 is a prime or not. It's actually kind of hard to factor 2021, okay? But if it were prime, A to the 2020 would be 1, A to the 1010, and then A to the 505, okay? So these are the numbers you're examining, and the minute you get something that's not, so if this one is not 1, you know this is not prime. If this one is not 1 or minus 1, you know not prime. If this one is not 1 or minus 1, you know not prime, okay? So let's let's see what happens. So, if anyone is still in chat paying attention, would you like to pick a random number between 1 and 2020 for me? Go ahead. If not, I'll pick one myself. It's not a big deal. So, let's see. Okay, I think there's a slight delay also there. Okay, 964. Sure, why not? So, let's look at 964. Okay, so I'm doing mod 964 to the 505 2021. Okay? Over. 2021 is not prime. How fast was that? So this is the power, this is the beauty of the Miller-Rabin primality test. Okay? Let me give you a few more details. These few more details are a lot less kind of elementary or easy to see. So 69 or 420, why not? Let's try them too. So let's do 69. Also proves that 2021 is not prime. So 420 also proves. But you need to calculate the power 505. It's a lot easier for your computer than you think. So for example, let's say that, here, let me, so remember, you're doing it mod 2021. So let me do an example if you've never seen it before, just to show you that, yes, doing powers would be really hard, but doing them modulo another number is actually not that bad at all. So for example, let's say you're interested in 3 to the 12th power mod 5. I'll do this for you. Actually, let's even make it bigger. Let's say you were interested in 3 to the 12 mod, I don't know, 7 or something. Okay? So this might seem like a lot of work. I mean, 3 to the 12th power is a huge number, right? So, I mean, for our brains, it's a big number. Let's look up what 3 to the 12th is. That's a big number, okay? 531,441. But the key is, if you're computing 3 to the 12 mod 7, that's not what your computer is doing, and that's not what you should do either, okay? Here's how this computation goes. You start with 3 mod 7, okay? 3 squared mod 7 is the remainder when you divide 3 squared, which is 9 by 7. So actually, this is the same as 2 mod 7. Because 3 squared is 9, and you take out as many 7s as you can, and that, I'm sorry, yeah, you take out as many 7s as you can, and that leaves you with a 2. Interesting, right? So that's why this never grows. This never grows as brutally as you would expect it to. So how about 3 to the 4 mod 7? 3 to the 4 mod 7 is just going to be the square of the previous result. So I know already that 3 to the 4 mod 7 is just 4, just 2 squared, which is 4. How about that? Okay, let me tell you what else. I know 3 squared is 2, so that means 3 cubed mod 7 is 6 mod 7. But then I know 3 to the 12, what is, well, actually, I shouldn't have done this. I should have done, let's do 3 to the 4 to the 3rd power. So let's just do 3 to the 8 mod 7. That should just be 4 squared, right? 4 squared is 16. 16 is, again, 2 mod 7. And let me know if I'm making any arithmetic errors. So I guess my point is that these numbers don't explode. Like, you can compute a very high power, and your computer, in fact, can do this instantaneously because these numbers actually don't explode, because you keep taking the remainder when you divide by 7 as you compute higher and higher powers. That's why for my computer and your computer, whatever you're doing, this is an instantaneous computation. It's not an issue at all, right? So because this happens, so let me finish. So 3 to the 12, okay, if I've done everything correctly, 3 to the 12 should, I guess, be 1, right? Because 3 to the 12 is 3 to the 8 times 3 to the 4, right? 3 to the 12 is 3 to the 8 times 3 to the 4, which is 4 times 2, which is 8. 8 mod 7 is just 1. Okay? So instead of having to deal with 531,441, in fact, you can get away with dealing with much smaller numbers. And just to show you I'm not lying to you, really is 1. Okay? So for a computer, doing something like 420 to the 505 mod 2021 is like nothing. It's like water, instantaneous. Okay? So here's the idea. So by the way, the Miller-Rabin test told us instantaneously that 2021 is not prime. So let's actually factor 2021 and see what happens. (43 and 47). That is a brutal factorization if you wanted to do it by hand, right? So as you can see, there are methodologies for figuring out if a number is not prime that are a lot faster than actually factoring it. I mean, you'd be sitting here for a while trying to factor 2021, right? Okay. I'm going to say something else about this Miller-Rabin test. So for example, what you do is, again, so for example, if you want to test if 2021 is prime, you just need to you pick a random number A, and then you do A to the 505, right? A to the 1010. By the way, A to the 1010 is just A to the 505 squared, right? So that one's not too hard to compute. And then you would do A to the 2020, okay? And you see if you have trouble over here. You know, if you're not getting ones and negative ones, you know for a fact that you're not dealing with a prime, because the only solutions to x squared being 1 modulo a prime are 1 and negative 1. That's what you're using here. So it's a very clever test. Okay. It is also, so I will point out, so if this fails, you know, if you're not seeing your ones and negative ones over here, if this fails, then you know the number is not prime. Okay? So I was able to very quickly conclude, very, very, very quickly conclude that 2021 is not prime using this test. However, there is a possibility, and people call it bearing false witness. People will say A is a false witness, which is kind of a fun term. So it can happen, and pay attention to the way I say this, it can happen that a number is a prime. It can happen that a number is not a prime, but all of these numbers are like 1 or negative 1 or whatever, right? That would be a problem, right? In that case, we would say that A is a false witness. So you know, you can get really unlucky with your random picking, okay? So you can have a composite number and also a situation where all of these are ones and negative ones, as they would be for a prime number. In that case, we would say that A is a false witness, okay? So now the question is, how many false witnesses are there? And so the answer is there's no more than, so if you look at all the numbers from like 1 to n minus 1, for any n, no more than a quarter of them will be false witnesses. So that's the big theorem that really makes this engine work, okay? No more than a quarter of these will be false witnesses, okay? Let me know if there are any questions about this. So there's no more than a quarter of these will be false witnesses. And there you go. That's why the Miller-Rabin test works so well. Because let's say you pick A at random and you do the test once and it works out. Well, I guess there was a 1/4 chance you got unlucky, but then you do it again, and then the chance that you got unlucky twice would be 1/16, right? And then you do it again, and then the chance that you got unlucky would be 1/64, right? And then you do it again, and the chance that you got unlucky again would be 1/256. So these probabilities go down astronomically quickly, you know? So for example, if you do the Miller-Rabin test 10 times, right? What is the probability that you were just that unlucky? That would be the probability. It would be literally 1 in a million chance that you got that unlucky. So just what if you did the Miller-Rabin test 20 times? That's 1 in, let's see, 1,000, a million, a billion. If you do the Miller-Rabin test just 20 times, just 20 different numbers, that's 1 in a trillion chance that you got that unlucky. And so in essence, these are the methods that your computer is using to kind of rule out numbers. So checking if numbers actually prime is hard, but ruling it out, you can rule out numbers very quickly using something like the Miller-Rabin test, and that's exactly what I believe the computer is doing. I mean, there are other algorithms that are similar to this, so to be honest, I don't know exactly what my computer is doing, but this is a pretty famous algorithm, and I am genuinely impressed at how simple and clever it is and how well it works as a primality test. So I'm just tremendously happy about this. So there you go. And so you just do this Miller. So let's try for another number. So for example, if we have let's try. If anyone in the chat wants to suggest a number, we can do Miller-Rabin by hand. Well, like almost by hand. We'll do the mod powers in a computer. But yeah, so that's why the computer is like in 0.00001 seconds able to tell me if a 3600 digit number or 4900 digit number is prime. So if you have any other numbers that you want me to test out, please just type them in. We can try it out just for fun. But if not, I also want to end off by sharing with you the video 299. Okay, I don't know if 299 is prime or not, but yeah, look, well, why not? Let's try it. So 299 is if you subtract 1 from 299, you get 298, right? Okay, how many times can you divide 2 out of 298? So this would be, let's see, so 1, 4, 9, only once. Okay, so the numbers, so for a random guess A, the numbers you would have to look at are a to the 149 power and a to the 298 power. Agreed? And your random guesses would be between 1 and 298. And every time you guess at random, it reduces the chances that, so you would multiply by a quarter, that would be the result. So I actually don't know if 299 is prime or not. So let's see what happens. So now we take a random guess. I'll take the first random guess. Let's try 2. That's 2 to the 149. Was it 149? Make sure I'm not being an idiot. Yeah, 2 to the 149, comma, 299. Oh, it's not prime. Just like that, it's not prime. Boom. How cool is that? So actually, yeah. What is its factorization? I don't know. Yeah, that's a rough factorization. So I mean, come on, that's neat, right? So 8008135. Let's try it. So 8008135. So I'm gonna subtract 1 and then see how many times I can pull out a 2, because this could be a lot. I don't really know about this number. So pull out a 2 once, only once. Okay. So 4004067. Okay. So, oh, it has 5. First sod with the with the quick answer over here. Okay, whatever. Even though, yeah, good catch, everyone. But okay, whatever. Even though we know, I'm still gonna use Miller-Rabin on it just to see, just to see how it goes. So I'm gonna take a random witness. So I don't know, 7, and do 7 to the 404067 modulo 8008135. It's not prime. It's not prime. Okay. All right. I'm gonna end this now. So yes, sometimes if you use your brain, you can see it faster, but it's a really cool way to test for primality. And of course, that's exactly what I did in order to get my cat prime over here, right? So hopefully the methodology to get the cat prime is clear. You just you start with an image, and then you I went over the code earlier about how you get a number that kind of looks like your image by seeing how bright the numbers are compared to how bright the pixels are in your image. And now it's just a question of searching. Now I made the claim earlier that because of the prime number theorem, if your number has n digits, If you choose an n-digit number at random, the probability that it will be prime is about 1 over 2.3n. And this is by the massive powerhouse bazooka level theorem called the prime number theorem. Okay, so this is very, very deep, very exciting, very, very technical stuff. Okay, but if you take an n-digit number, there's about 1 over 2.3n chance that that number will be prime. Okay, fantastic. And now, what do you need to do is, so basically, if I just keep guessing n-digit numbers, it will only take me about 2.3 times n guesses before I pick a prime number. So in our case, we're doing a 4,900 digit number, and I'm just going to keep adding small random numbers to it, essentially, until I have a prime number. So let's see. I have written this code so that my computer will print out every time it finishes 100 guesses. So every time it guesses 100 things, it prints out 100, and then when it guesses 200 things, when it's done with 200 guesses, it'll print out 200, 300, 400. This will allow us to keep track. So I've started with my cat number, and I'm essentially adding random numbers to it, random numbers that aren't too big, that won't compromise the integrity of the image, right? And presumably within, like, what is it, 2.3 times 4,900, somewhere around 11,270, maybe a bit before, maybe a bit after guesses, it should be able to find me a cat prime, which it did. That's why it became the thumbnail, but I kind of want you guys to see it too. So hopefully what I'm doing is making sense. Okay, you run the code, and then you know, it just keeps adding, you know, random numbers, and it's just guessing with their, you know, and then it does something like Miller-Rabin to see if it finds a prime or not. And Miller-Rabin is so fast at ruling out the ones that are prime, that aren't prime, that's why this fundamentally works. So hit enter over here. Okay, I hope, by the way, if my stream dies right now, it's because my computer is suffering, and I'm very sorry that this is happening. Okay, so my computer's already done with 300 guesses. I mean, come on, that's so fast. Like, I'm always amazed by stuff like this. Like, that's insane. Like, it's already done with 600, it's guessed 600 numbers that are all 4,900 digits long, and it has already tested whether they're prime or not. Come on. How crazy is that? It's insane. It's completely insane. So I told it to add a random number from 1 to 10 to the 10. So the only digits that'll change are, so the only digits will change are like the last 10 digits. And that's how the randomness is working. Okay, so my computer has made 1,500 guesses. And once again, apologies if the stream dies. It'll die because it might die because my computer might overheat or something like that. I put no brakes on this code, you know. The way I have it set it right now, it's just like use whatever resources you can find, which is a pretty brutal thing to do to a computer. There are ways to put the brakes on it, but you know, whatever. We're in this now. We're in it to win it. So okay, it's already done 2,000 guesses. I guess I might leave this alone. I want to share with you. You know, while it continues to guess, I do want to share with you the video that inspired me to do this. And it was a number file video, actually. Let me show it to you. So let me unmute the... Okay, so this is the number file video that I found that inspired me to do this. Also, let me turn off my own music so that we can... Actually, maybe I'll leave it on so I don't get content ID'd. So... Okay, let's so
wiped out the entire lawyer generation.
Yeah, I'm not gonna watch the whole video, but this is a gift that someone gave to Trinity Hall. I believe it's in Oxford, and this is a massive prime number that is meant to look like the logo, or I guess the emblem, or I'm not really sure what to call it. The coat of arms, I guess. I don't really know. So this thing is meant to look like, you know, the the coat of arms of Trinity Hall at Oxford or whatever, and it's a prime number. Okay, so this person, whoever it was, if you watch this video, you can see who this person was. But yeah, it's kind of beautiful. You can see the image over here, and yeah, there it is. So I'll turn off the subtitles. So this person found a prime number that looked like the whatchamacallit, the coat of arms at Trinity Hall, and the number of digits in this prime. Pause the video. Heartbroken that I couldn't watch this later. Okay, I'm sorry to I'm sorry to hear that. I don't know. Some of the videos get a little scuffed. I don't know. The YouTube system has not been the kindest to me. I'm sorry to say, but more on that later. Fubagork, thank you for joining. But what I was trying to say is that this person created this prime number, this Titanic prime number, and it has the same number of digits as the founding year of Trinity Hall, and the prime number looks like the logo the emblem or the coat of arms of Trinity Hall. And so this is what inspired me to walk down this particular path. And it's amazing. So whoever this was did it with the computational power that existed in the 1970s or whatever. So that's more impressive. Like, you know, now we have our Ryzen 9s or whatever, and, you know, our crazy graphics cards, and computational power isn't as much of an issue anymore. But things like, I don't know, when was the Miller-Rabin test created? Let me look it up. The Miller-Rabin Primality test has been around since 1976. So there's a chance that this person, whoever made this picture, knew about primality tests that were, or maybe something similar. Maybe not exactly the Miller-Rabin primality test. I have to say I'm in love with that primality test. Also, my computer is done. It took only 5,200 guesses to find me a prime number. This is the prime number. This is a massive prime number. And if I, let's see, look at this prime number, let's see, in a grid, I get a cat. That's really it. And as I was mentioning earlier, what I did to make this look nicer in Photoshop is I made the digits a lot closer together. So there's just a lot of white space between all of the numbers, which is kind of compromises the cat integrity of this picture, which is kind of awful. But you know, you can see the cat in there if you like, if you shrink this down. Okay, so the takeaways for this video that I really want you guys to take away is how amazing the prime number theorem is. Because, of course, the prime number theorem does not just tell you that there is an infinitude of primes. It doesn't just tell you that there are infinitely many primes. What it tells you is that it tells you how frequently the primes occur. And it's amazing that they occur so frequently, that we understand something like that about prime numbers so well. You know, that's kind of shocking. You know, I'm definitely not an analytic number theorist by any stretch of the imagination. So stuff like that is really, really, really shocking to me. Okay. And then the other half is that we have these amazing, amazing primality tests that tell us very quickly when a number is not prime with very, very high probability. So as I pointed out, that, you know, if you just do Miller-Rabin 20 times on like a really big number, you already know, like within a probability of 1 over like a trillion, whether that number is prime or not. How about that? Okay, I'm very excited, and I really love doing this. I did this last night, and it made me very happy. Let me know if you want the code, if you want to mess around with it yourself. If you try it, please let me know. I'm probably going to tweet something out about this. I haven't been on Twitter in literally years, so I need to get on that. I mean, some of this stuff is pretty cool. I think more people should see it. So if you experiment with this, if you play around with this and you're able to produce something beautiful or interesting, please let me know. I would absolutely love to see it. And if you need any help, you could just do it with this code. I don't really care. So like, if you want this, let me know. I'm more than happy to share it as well. But other than that, I think that's it from me today. Thank you so much to everyone who decided to our Mathematica, but sharing it would be cool anyway. Just so you know, this would not be hard to do in Python as well. In fact, I tell you what, you can cheat right now. If you use the same font as me, then you can use this exact table of brightnesses and write it in Python. So let me tell you the name of the font that I used, and that way you can use this exact table of brightnesses to translate your images, because that's the hardest part. Because Python already has a primality tester that's lightning fast, right? Because they're all based on like the algorithms like Miller-Rabin and stuff. So like Python libraries already have like incredible primality testers. Everyone does now because they're so good and they're so easy. So if I let you know what font I'm using here, you can just cheat and use the same brightness table to translate your image into numbers. So let me just figure out what the Mathematica 11 default font is, and then you can use the exact same thing, and then you don't need any code at all. It's like not even like that's the only part here that's unique to me. Everything else is just like nothing. So what is the name of the Mathematica 11 default font? Not Courier. Okay, it's a font called Consolas. It's kind of weird. I don't know. So the name of the font I used is I don't know if it's like harder to find this font or writing your own brightness table, but the name of the font is Consolas. And then you can use this exact brightness table that I used for my digits, and that'll save you like half the work in doing this. So let me know if there are any other questions. Actually, if you let me know what font you're interested in, I could quickly like put that in and give you a brightness table for your favorite font. But whatever. I should stop now. It's been it's been more than an hour, and I've learned that people's math tolerances are they're only about, you can only talk about math for about an hour before people start getting tired. So once again, thank you to everyone that showed up. I really, really appreciate it. I hope you enjoyed it. I'll be having more fun again on Saturday at 1 p.m. as usual. Love you all, and peace.